It is my pleasure to announce Hong Kong talk. He will tell us about dynamical mechanism for the page curve from quantum chaos. Please, 45 minutes. Okay, please.
Okay, yeah. Thanks a lot for the invitation. Yeah, it would be nice to come to Moscow, but still, yeah. So I'm going to talk about some recent. 1 second. How I cannot move the slides. Yeah. I'm going to talk about some recent work with Shreya Vadhan. These are based on some recent papers which appeared in December, and also one in February this year. So recently there have been exciting progress in showing that the entanglement entropy, say, of an evaporating black hole and its Hawking radiation follow the page curve, and which provide the strong support for unitarity of the evaporation process. So we have already heard various talks about such calculations in this conference. And so where actually few of us thought actually black hole follows the rules of quantum mechanics, but nevertheless, it was a pleasant surprise that fine-grained quantum information encoded in the page curve can actually be captured by semi-classical gravity analysis. So on the one hand, we can be awed about the power of semi-classical gravity, but on the other hand, we can ask the question, why? Somehow, why in this case, somehow so the fact that somehow semi-classical gravity can capture such information should also tell us something about the system itself. Yeah, because if the information is really very detailed, then we will not expect semi-classical gravity to see it. So normally, say semi-classical gravity analyses are very good at capturing physics around the saddle points or different saddle points, say change of dominance between different saddles, etc. And with each saddle point, say representing distinct physical processes. The recent derivation of the page curve also have a similar flavor. So the switch, so the key about the page curve is that there's a turning around in the entanglement entropy, say, of a black hole or the radiation at the page time. And from the gravity analysis, such a turnaround happens from a switch in the quantum extremal surfaces at the page time. So even though this is not exactly the kind of saddle point analysis, but they have a very similar flavor. Somehow the quantum extremal surfaces represent a different contribution of the entropy. Somehow they change dominance. So that the page curve can actually be captured by such semi-classical analysis should suggest that somehow there should also be a switch in the dominant physical processes at the page time. And this is also strongly suggested by the recent, say, Euclidean replica wormhole analysis. There indeed this kind of emergence of the page time and turnaround came from, say, contribution of a different saddle point, which people call Euclidean replica wormholes. And so the larger question would be, what are these physical processes which somehow this switch, quantum extremal surfaces or Euclidean replica wormhole such kind of different saddle point they capture? So in this talk, I will make a proposal based on our recent understanding, say, of quantum chaotic systems. I will assume, so here I will assume that black holes are actually governed by quantum mechanics. And in fact, they are governed by highly chaotic quantum many-body systems. And then I will discuss a new signature of quantum many-body chaos, and then use this new signature to discuss what are the physical processes underlines this turnaround at the page time. Yeah, turnaround of the entanglement entropies at the page time. So this should shed some insight. This will shed some insights on the macroscopic physical interpretation, say, of those quantum extremal surfaces, and also potentially the replica wormholes, etc. And this should also shed light on how the information of a black hole is transferred, say, to the radiation. So before I start reviewing a page's original argument for the page curve, let me pause for questions. Do people have any questions so far? Okay, good. So so let me just quickly review the original argument of page. So let's just consider a quantum system which consists, say let's call the whole system to be L, which consists, say, of the union of two subsystems, which I call B and R. So eventually this will be a black hole subsystem, the radiation subsystem. And then the Hilbert space have such a tensor product structure, and the total dimension of the Hilbert space is given by the dimension, say, of the B subsystem times the dimension of the R subsystem. And then, say, now let's consider, say, some pure states in this full system, and then take any pure state, then we can calculate the entanglement entropy, say, associated with the subsystem B. And then now suppose we average of all pure states, okay, of the full system. And so this bar, SB bar here means the average. And then a famous results from Lupkin, Lloyd, and also Page is that this average entropy for the subsystem B and subsystem R, of course, they should be equal because we are considering the pure states. And then they just given by the minimum between the cross-grained entropy, say, of the B subsystem and R subsystem. So this cross-grained entropy I defined just for this kind. I will always just consider finite dimensional Hilbert space. So the cross-grained entropies for this finite dimensional Hilbert space case just corresponding to the logarithm, say, of the Hilbert space, say, for the B subsystem, and the logarithm for the dr for the R subsystem. And this formula applies in the regime which dB and dr are much greater than 1, and also dB are not equal to dr. Say, when dB is, say, of the same order as dr, and then there are sub-leading corrections here, which I will not be interested in. Good. So this notation, squid, SP, and SR, I will use often in subsequent discussions. So keep those notations in mind. So now let's consider a simple model for the black hole evaporation, which was essentially a Page originally considered. So let's just consider this L, say, have this B subsystem, union of a B subsystem and R subsystem. But now those systems change with time. Okay. So at the t equal to 0, so everything is inside the black hole. So the black hole is the full system. And then as time evolves, some part of the degrees freedom in the original black hole system goes into radiation, and then the degrees freedom in black hole system decreases, and that in the radiation system increases, and then etc. Okay, so B continues to shrink, and the number of degrees freedom in R continues to increase. And the detailed mechanism, say, how the degrees freedom goes from B to R is not important. Just the fact that somehow the relative number of degrees freedom between them changes. Of course, the total system remains the same as L. Okay. Yeah, so this is just a very simple a model for the black hole evaporation. And now, say if one assumes that the full system, say L, is in the typical state, which means that somehow the average behavior can be in the sense that inside the typical state, the actual entanglement entropy you calculated for the B subsystem or the radiation subsystem, they actually have the same behavior, say, as the average entropy. And then in this case, then you derive this so-called page curve, and then the evolution of the BT and the RT as you change, as the time evolves, because the BT continue to shrink and RT continue to increase, just given by the minimum between these two. So roughly, if you look at the cross-grain entropy for SBT, and that just decreases with time monotonically because the black hole keeps losing degrees freedom, and similarly the cross-grain entropy for the radiation increases monotonically until all the degrees freedom has come from B to R. But the actual entanglement entropy follow from the minimum of these two, then follow this curve, this real curve, and then turns around at this page time TP, and which is which is roughly the degrees freedom between this B system and R system become equal. Okay, and so this was the page curve, and this is the key turning around point. So now, Page's argument is very general. It does not need any details of the black hole plus radiation system. So as far as the evolution is unitary, okay. And so so we don't even have to ask any details of the system. And so that's why this argument is very powerful. But here there's a highly non-trivial assumption, is that the black hole is in the typical state. Okay, by typical state here, by definition, a typical state here, it just behaves as an average state. You just say when you look at say take any subsystem of your full system, take any subsystem A of your full system, and then the entanglement entropy for A would be corresponding to the minimum between the, say, cross-grain entropy of the A and that of the A bar. So A bar means the complement of A. Okay. So essentially here, the key is that black hole should be in such a typical state. So this assumption can also be posed as a dynamical question. Okay. So what the property should the Hamiltonian governing the evolution of a black hole should satisfy, so in order to ensure that the black hole is actually in the typical state. Okay, and so this is the question I'm going to address, and in the process of trying to understand this question, and that also will also shed light on the issue why somehow this page curve behavior can actually be subject to semi-classical analysis. So black holes are believed to be governed by highly chaotic systems. And just from the basic intuition that somehow a black hole absorbs anything, and anything when you go to the black hole, it just lost. And just like in highly chaotic systems, when you throw something, add something to a chaotic system, very soon the chaos will spread the original information through the whole system. And also for the last few years, we have learned a lot between the connections between the black holes and the quantum chaos. And one aspect which has been discussed a lot during the last few years is the growth of operators under the Heisenberg evolution. So it turns out that the growth of operators can be used, say, to distinguish the chaotic system and say integrable systems. So recently we found a new feature, this operator evolution, which was not discussed before, which we called void formation. And based on this concept of the void formation, we also identified the new signature of quantum chaos. And so I will show that actually this chaotic void formation provides a dynamical principle for, say, for quantum system evolving towards the typicality. Okay. Good. So yeah. So now I will talk about this void formation and quantum chaos. So let me just pause for any questions. Okay, good. Okay, so for the last few years, we have learned a lot about the operator growth. So cartoon picture for the operator growth is the following. So let's imagine this circle, the region inside this circle, this black circle, is your space of degrees freedom. Okay, say this can either so this space can be internal space, can also be physical space, etc. And now, if you consider, say, some operator which originally only localized among some very small subset of degrees freedom in your space of degrees freedom, and so as time evolves during the Heisenberg evolution, and this operator will become, say, in the typical quantum many-body system, this operator will become more and more complicated, and in the sense start involve more and more degrees freedom of your system. Okay, so this operator will grow, and eventually around this so-called scrambling time, and this operator will eventually cover, say, the full, essentially all degrees system, all degrees freedom of your system, and so we say this operator has been fully scrambled. Okay, and from the way how this operator grow, and then one can distinguish between the chaotic system and the integral systems, etc. So in physical space, and this such growth of operator is often reflected as emerging the light cone. So suppose you start, let's just consider one-dimensional case. Suppose you start with some operator localized at x equal to 0, and then as time evolves, the support of the operator, the non-trivial support of operator, will span a light cone, okay, say defined by the so-called butterfly velocity, and then the operator become supported in a larger region defined by this light cone. And okay, so during this process, we argue actually there's something else going on, which we call the void formation during this operator growth. So the heuristic picture is that if you start with some operator, again, this circle heuristically denotes it's a cartoon for the space of your degrees freedom of your system. So if you consider some operator originally just, say, concentrated, supported only in some subset of degrees freedom, and then we know after the scrambling time, so this operator will essentially cover the all degrees freedom. Then, of course, in general, under this Heisenberg evolution, this operator become a very complicated operator in the sense that this has become a, say if you can expand this operator in the basis, say in the basis, say familiar, convenient for your physical analysis, and when you expand in that basis, and then this evolution will involve in larger and larger of operators when you expand this operator in that basis. Okay. So what we want to argue, actually, not only such a say operator cover the full space, not only this process going on, and it can also happen that this operator develops some voids, say in some subsystem A, in the sense that the operator is supported only by the identity, has low support in some subsystem A. Just say here is just identity. and you have non-trivial support outside in a bar. So if I write it in terms of the equations, and then this say this original operator O at some time t, OT, then can be separated into two parts. And this two part, this O1T, have the structure which is the identity in this subsystem A, and then some non-trivial operator, say in the complement of A. And then the rest, I call it O2, and just denote these generic operators. And this O2, of course, is defined to be orthogonal to O1 in the sense when you take the trace of a partial trace in the A subsystem, say this O2 is orthogonal to the identity operator, and the trace has to be 0. Okay. And so we know that for say when you have a finite dimensional Hilbert space, the space of operators themselves also form a Hilbert space. And then we can actually then define a probability for this void formation just by defining an inner product. Yeah, just using the inner product of this operator Hilbert space. And essentially that just corresponding to, say, trace O1 dag O, and then you divide it by the normalization of your original operator. Okay, and then this can be used, and then this defines the probability, say, for some operator O to form a void, say, in the subsystem A. Okay. So here is an example, say, for void formation in the one-dimensional spin chain. Say previously we had this heuristic picture that if you have a local operator sitting at x equal to 0, and then as time evolves, it will fill some night cone. But here I want to argue, actually within this night cone, the operator is actually not necessarily supported everywhere. There can be gaps. Say there can be identity operator. There can be this void in different places. So now I'm going to show you a simulation of a spin chain system, and you will see this void formation clearly. And so this is a simulation, say, of a spin chain. Say if you start with a spin, with a non-trivial spin sitting at x equal to 0, and then at the beginning you have identity in all other spatial locations, and then you just evolve this operator with time. Here we actually evolve it using some kind of integrable circuits. And anyway, it's just some unitary transformations, some discrete unitary transformations. And you see, actually, so the black color in this plot means that the spatial locations which this operator is non-trivially supported, and say with non-trivial sigma x, sigma y, sigma z, etc. And then the white region then corresponding to the identity operator, corresponding to this void. So you see, actually, for this particular example, you see there are actually many voids formed. And actually, in this case, they form some kind of fractal pattern.
Sorry, Hong, I have a question.
Yeah.
So
okay.
Typically an operator will evolve into sum of products, right? So there will be a sum, and then in each term in the sum, there will be some product over all sides.
That's right.
Is the claim that in all terms in the sum, the locations where you have white will have identity?
No. Say if you look at this this equation, and typically they don't. But you have, in general, this operator is a complicated sum of many operators. Say if you express in some basis, and so in general, for example, this A2 does not have any does not have a void in A. It may have void in some other places, just does not have a void in A, and then those with void in A just corresponding to a subset of operators. And so this is a good question you're asking. So this example I'm showing you is a very special example, which actually so this is called Clifford circuit. You can actually write down this operator. Just a single operator. Time evolution, you just get a single complicated operator.
I see. So in this picture you're drawing, you just have a single product. There is no sum of products.
That's right. Yeah, just single, rather complicated. Yeah, this time. Yeah.
Okay, thanks.
Could I follow up on that question?
Yeah.
So in the usual evolution, you're getting this sum, and there are different kinds of products, and many different operators appear, and they may have support across the whole string or in isolated locations. What's really special about this operator O1, or when is it important for your discussion?
Right. Yeah.
My attention on that particular operator.
Yeah. That's a very good question. So this A can be chosen arbitrarily. I'm just say you design. Say you ask for any subsystem A, and then the claim is that there always exists operator like this. There always exists a part in this complicated operator which contains the void in A.
Yeah.
And then yeah, this is just a statement. And then later we will show, if you are interested, say in the entanglement entropy of A or A bar, and then such operator, such kind of operator which have void, then plays a very important role.
Okay, thank you.
Excuse me, may I ask you, your void system is has a special, has a system of special symmetry. Is it correct? Can you say what spin system is behind of your calculation? Is it exact integrable or not?
Right. Yeah. This particular example indeed is one of the Clifford circuits, and which is it's a very so this is say this is the Hamiltonian evolution. This is a discrete set of the unitary transformations, and say you have t equal to 0 and t equal to 1. You act on the system some set of unitaries, and then at t equal to 2 another set of unitaries, etc. And indeed, this Clifford circuit, those unitaries are chosen. The system are more or less integrable. Yeah. So this is this can be considered as an example of an integral system. Yeah. Good. So just by very simple quantum mechanical argument, one can show this void formation process is actually required to occur by unitarity. So you can show just for any system, take any subsystem A, and then you look at the average probability, say for forming a void, say in some subsystem A, then over all initial operators, and then you just average over them, and then you find that this is just given by 1 over dA squared. And the dA is the dimension of the Hilbert space of A, okay, for this subsystem A. And so this behavior is very easy to understand. So dA is the dimension of the Hilbert space of A, and the dA squared is essentially the dimension of the Hilbert space for all operators in A, okay? And now, when you have void formation in A, means you have the identity operator in A, and the identity operator is just a single operator among of all these dA square possible operators in subsystem A, and then you just get 1 over dA square. Okay, so this is a just very simple. You just get this very simple behavior. Essentially, this is a kinematic statement that works for any system, whether it's chaotic or integral. So for chaotic systems, so from our earlier studies in this December paper, in random unitary circuits, which can be considered as say a very simple model for chaotic systems, and from those studies we made a conjecture that for in the chaotic system for generic operators O and the subsystem A, actually the probability to form a void in A for such an operator O is also given by this 1 over dA squared. Okay, and yeah, and the assumption is that the dA have to be much, much greater than 1, and also this was sufficiently large T. Okay, so yeah, so you can check, so you can derive this behavior from explicit calculations in this random unitary circuit, and so we conjecture actually may work for all chaotic systems. So we also have some numerical studies for some, say, some chaotic spin chains, etc. And we see some partial support for this. But since we cannot do it's not easy to do a very large system numerically, so we don't have very conclusive results yet. Yeah, but we see some support again for this behavior from real Hamiltonian chaotic systems.
Sorry,
Anyway,
question.
Yeah. So
does this follow directly from ETH?
No, this does not follow from ETH. In the sense, this is rather different from ETH because we ask very different questions. This is in some general. This is in some. This is here. There's no states. Here we're not talking about any state. This is a statement about just operators.
I see. Thanks.
Yeah, and eventually we will use this for, say, evolution. Yeah, this will have say implications when you evolve from some generic initial state, etc. Yeah, but this is a statement about operators. And so we call this random void distribution. Yeah, because the
Can I ask a question, please?
Yeah. Yes.
This seems like saying that it's like there was a discrete space where you associate one operator for each dimension of the Hilbert space, but typically you will get it's a continuous space, right? You have a combination of all the operators, so the probability of getting a specific operator should be always 0, no?
Oh yeah, you say in the for example in the quantum field theory.
Yeah.
Yeah. So here I'm talking about the system, say with a Faraday dimension, the Hilbert space, and then you can make those notions exact. But for systems, say like a quantum field theory, or system with infinite number of degrees freedom, then there's always, say, in physical situations, say there's always some kind of a constraint, say from because you can only consider some finite energy states, etc. So effectively, and the dimension of the Hilbert space, which is relevant for physical consideration, are also finite, and also you can also argue the relevant operators are also finite. Of course, to define those things exactly mathematically, rigorous mathematically become more difficult. And so, so here I'm just restricting to a finite dimensional Hilbert space. And for infinite, for the infinite dimensional Hilbert space, and then of course requires more technical work. Yeah, but I think a physical picture should still apply.
Thanks.
Good. So we will call this a random void distribution. And in contrast, when you have an integral system, and then the probabilities actually depend on sensitivity on the operator rho, this operator O, and the subsystem A. This you can check easily. Just say, for example, taking a free series, and then you can just evolve it, and then you see actually, a free spin system, etc. And again, let me just show you this picture. And this, as I mentioned, is corresponding to an integrable circuit. And you see this void formation is certainly not random, and there's it's pretty regular pattern. And also depend on sensitivity on the operator you use. And if you use a different operator, and then you will see a different pattern. Okay, so now let me just very quickly, before I talk about the relevance of this void formation, let me see how much time. Maybe actually I'm running a little bit short time. Let me just skip this. So the point is that actually this void formation can have can be very useful when you consider, say, systems. Say if you are interested in the entanglement entropy for some system, say after the global quench, etc., and then this void formation can play a very important role, and also can be used to generate multipartite entanglement, etc. So let me just go directly for the black hole story. So let's again come back to this Page's model, and this simple Page's model, and then you can see the at the beginning you have black hole, then some degrees freedom goes to the radiation, and then more and more degrees freedom go to the radiation. So now let's consider, suppose at t equal to 0. So let's say the system is in the pure state, okay, and say this could be a star before the gravitational collapse, okay. So this is in general some maybe highly far from equilibrium initial state like a star, and then rho 0 is the density operator for the full system, which is a pure state, and then I can decompose it in terms of the identity operator and then the traceless part, okay. And the reason we decompose in this form, because under the time evolution, so now we can just treat the evolution of the system as a Heisenberg evolution of this operator, okay. And so the reason to do this separation is that identity operator, of course, does not evolve, and the non-trivial evolution only in this traceless part. And then at time rho t, and then I can say, and the Heisenberg evolution, then I can again have this identity part, and then this traceless part involved into some rho hat t. So now, since I'm interested in this B, the black hole subsystem and the radiation subsystem, I will decompose rho hat t into the following form. Yeah, this is just a kinematic statement. Say rho t I decompose into the identity operator in the B subsystem, say tensor with some operator in R, and OB in the OB with some non-trivial operator in OB, and then tensor with identity in R, and then both things are non-trivial. Okay, and in order not to overcount, of course, this OR should be orthogonal to the identity operator, because the identity, because if the identity operator in here is already encoded here, and similar with OB and etc. So none of those OB OR and the tilde OB OR, they contain identities. And also just from the notation convenience, I will suppress the time dependence. You should keep in mind this BR, the definition of BR, they change with time. And so this is what we call the void formation. So this is the void formation in B, and this is the void formation in R. Okay. And so all these non-trivial operators I said, OR, OB, tilde B, and the tilde R, they have zero traces in respective subsystems. So now, if we are interested in the reduced density matrix in B and R, and then you just take, say, in this case, you take trace over R, and because those traceless properties, then only the identity part, say, which give you this, and then the void formation in R survives. Okay, so this one, when you take the trace in R, then give you the dimension of dr, and then you have this OB, and everything else they drop out outside the trace. And so we see that the reduced density matrix for the B subsystem is related to the void formation in the R in its complement in the radiation. Okay, and the same thing with R. Say rho R is related to the identity operator, and then the void formation in the in B. Okay, and so that give you the reason why we are interested in the void formation, and why we are interested in the probability in going to those void formation operators. Okay, and and this identity part just comes from this identity part. So now let's concentrate on the radiation subsystem, and the same story can be said for the B subsystem. Yeah, just exactly parallel story. So now let's calculate its second linear entropy, which is very simple. You just calculate the trace rho R squared. And then you have two terms here. So one just comes from the identity term, which just gives you 1 over dr. And then you have another term which is giving you this OR square. And I can actually rewrite this in terms of the probability, say, of developing a void in B. As I mentioned, this term just comes from developing a void in the black hole subsystem. Okay, so I just can, yeah, just with one line, you can show this, the square of this OR is related to dB, with the dimension of the B Hilbert space, and the probability of forming a void. And yeah, so this comes to that term, and this comes to that term. And the cross term is 0 because OR is trace. So now we can just use the random void distribution, and suppose this system is chaotic and satisfy the random void distribution, and that tells us this is just given by 1 over dB squared. And then we find the second Rayleigh entropy just have this simple behavior, 1 over dr plus 1 over dB. And if you write it in the cross-grained form, in terms of cross-grained entropy, and then this is just exponential minus SR plus exponential minus S. Okay, and then immediately you find S2, the second Rayleigh entropy is given by the minimum between the two. Okay, so let me just make some remarks. So here, the transition in the page curve, which go from SB to SR, etc., comes from the change of dominance between the identity and the void formation parts. Okay, just come from that. And second, so let me translate those quantities in terms of gravity language. Say, suppose this system actually corresponds to a black hole. And then at early times, this radiation, of course, is of order G Newton to the power 0. This is corresponding to a perturbative process, which the black hole emits radiation. And this, the cross-grained entropy is of order Gn0. But the cross-grained entropy for the black hole is just the black hole horizon, and that's 1 over Gn Newton. So at early times, this one is order 1, but this one is exponentially suppressed. Okay. And so the void contribution is non-perturbative in Gn and exponentially suppressed, say in early times. So at early times, then it makes sense. We just forget this part because this is just non-perturbative. Okay, it's non-perturbatively small. But if you wait until the page time, eventually this becomes sufficiently small, then these two become competitive with each other. Then after page time, and then this void formation part dominates. Okay, and so at least for this second Rayleigh entropy, you can actually match this calculation exactly with the the calculation of the replica wormhole in this paper by the Stanford group, which they have a very simple calculation for the JP gravity, and in which this void, what we call the void formation part, just come from the contribution of the replica wormhole. So you can now also you can also try to generalize this discussion to higher Rayleigh entropies, and in our papers which appeared, we only consider the second Rayleigh entropies. And so you can generalize to higher Rayleigh entropies. When you look at higher Rayleigh entropy, you just take some higher power of this. And so now it's actually not enough just to talk about the probability of the void formation, because probability only involves the trace of the second power, say, of the void formation part. And so you actually need the higher moments of this void formation part of the, you need the higher moment of those parts. But you can make argument, and if you substitute this explicitly into here, and now you get more complicated contribution, because now the cross term between them no longer vanishes when you have powers n greater than 2. Okay, so you have the part come from the identity, and the part solely come from the void formation, and then you also have the cross terms. Okay, so but you can but you can argue actually before the page time, again just this identity part dominates because this is the perturbative in G Newton. And then after the page time, only this term dominates. Okay, this term dominates, and we actually have answers which can match exactly, the behavior of these can match exactly with those from the replica wormholes in this in the JT gravity in this Stanford paper. Okay, So let me just summarize the bottom line here. Is that the say if you consider your initial density operator for your black hole system, say this is the star. So on the time evolution, if the system is chaotic, and then this it will develop some probability. Yeah, then we'll have some probability to develop the void in black hole system and in the radiation system, and those void deformation are relevant for the non-trivial parts of your reduced density matrix, and the key is that these two parts changes dominance at the page time. And the remarkable thing about the chaotic system is that actually the non-trivial part of your reduced density matrix actually has some universal behavior, which you don't need to know the details of the system. Okay, you don't need to know the details of the system. So in the cartoon picture, this void formation part is just like the following. So suppose you consider at the beginning you have some 0 hat, which is a non-trivial operator, which involves the full degree freedom of your system. But now the non-trivial, this void formation part comes from the process which somehow the operators which originally in the black hole part, somehow they all jump into the radiation part, and with the just identity operator in the black hole part, okay? And somehow just like the operator jump out of the black hole, yeah, just heuristic. Okay, so you can, yeah, let me look at the time. Okay, yeah, I'm actually running over the time. You can also, yeah, let me just quickly finish my last few slides. So you can also look at the information transfer from the black hole to the radiation, for example, by considering this so-called Hayden-Pressure process. And then, anyway, and then in this case, you can already, let me not go into detail here. You can show that again, that the void formation provides the dynamical principle for understanding how the information actually transferred from the black hole to the radiation. So heuristically, say you have this operator which originally in the black hole, then after the page time, then they jump into the radiation part, and that probability dominates after the page time. So that's why the information from the black hole to the radiation only happens after the page time. So in our paper, we also consider slightly more complicated black hole evaporation model than this page. Yeah, you can put a little bit more structure in the model than what Page considered. So here we consider some kind of spin chain, some generalized spin chain, which each degree freedom, say which each side corresponding to some generalized spin, and then you just imagine at each time step, a certain spin then become the radiation. Okay, and again in this, you can put more structures here, and again you can show that the void formation controls this. It's responsible for this turnover at the page time, and guarantees the unitarity of evolution. And also you can consider, motivated by this discussion of Mary, Mahajan, Maxine, or you can also consider a model corresponding to, say, a quantum mechanical model corresponding to internal black holes coupled to some bars. And you can consider, say, anyway, you can also consider in that case, and then here the physics is more complicated. Okay, so you can consider, say, black hole, consider two initially maximally entangled identical systems, and then each of them coupled to a bars. And for the bars, you can either be free or chaotic, it doesn't matter. And then you take, say, for example, the bars to be a product state. Yeah, also the details of initial state is not important. And then you just involve the system, and then see how the entanglement entropy, say, of the black hole and the bars evolve this time. So here the physics are more complicated. So one can again study, say, evolution of entanglement entropy and information transfer from the black hole to the radiation, and so analysis. So this kind of quantum mechanical analysis again provide insight into what kind of physical processes, such say quantum extremal surface or replica or wormhole are capturing. Okay, and say in this case we can again decompose the density operator of the full system in terms of tensor product of those black holes and the bars, and then again you can make the similar argument. We're not going to detail. I will not have time to do that. And let me just quickly mention that here there are three processes going on. So one process is an operator originally. Say let's consider a cartoon picture, which the black hole diffuse freedom corresponding to diffuse freedom inside the circle, and the bars diffuse freedom corresponding to the diffuse freedom outside the circle. Okay, because now the diffuse freedom don't change in this internal black hole model. So then there are several processes can happen. Say original operator localized inside the black hole, they can grow on the time evolution to cover both black hole and the bars. You can also have an operator which originally outside the black hole, and then just grow inside into the black hole. And also you can also have an operator which are both in the black hole and in the bars, and then on the time evolution they develop a void in the black hole. Okay, so if you just analyze those processes, and then you can work out how the entanglement entropy evolve with time. And then you find this page curve like this, which was also found in the gravity calculations. So here you actually find that this perturbative increase in the entanglement entropy. Say, for example, this is the one for the one for the radiation. The black hole is the same. So if you look at the entanglement entropy for the radiation, then you find the part which dominates this increased part is this process, which is the bars. The operator in the bars, they just grow into the black hole part. Okay, so this is a perturbative process, and the perturbative in G Newton, and then that leads to the entropy growth. And then you have this process corresponding to the developer void in the black hole, and which is non-perturbative in G Newton. And so this is exponentially suppressed in this part, but become of order 1 after the page time, so after this time scale, and then these two processes essentially compete to give you this constant. Okay, and this is also exactly what happens in this in the gravity analysis from the island and the replica wormhole contribution. You have a competition between the perturbative and then this non-perturbative process, which then in the end give you this constant. Okay, let me just conclude. Let me just show the summary here. Let me just, thank you.
Okay, thank you very much for your very instructive talk. Please, any questions?
I have a question. Hi Hong, have you studied this void formation in the SYK model, let's say for some finite n, like 30, 35?
We are trying to study this. We are trying to study that, but we haven't. One can show, at least based on some earlier literature, we can deduce that the void formation also happens. This random void distribution also happens for the SYK model. At least for time sufficiently large, but we are still looking at it.
Okay, thank you.
More questions, please.
Hi, Hong. So if you go back to the derivation of the slide where you had 1 over dr plus 1 over dB.
Okay.
You're still averaging over the OB, right? So you're assuming some kind of typicality of OR?
No, we are not doing any average. So this should compose, let me just come back to that. So we are not doing any average. So this is just this rho R should come from, this rho R just should come from generating, say, Hamiltonian evolution.
Right.
And then essentially when you calculate the second entropy, you have to calculate this OR, trace OR squared.
Right, so we are assuming some typicality of this OR, that it's equal to this probability.
So that is guaranteed. So this probability is not average. We just call the trace OR we just from our definition. Yeah, let me just go to earlier. From our definition, there's no average here. So in this definition, so this probability, when we call this probability, this just tells you the relative weight of this O1 square divided by, say, O square.
Right. But in general, this should depend on A, right? What operator or O operator.
Right. Yeah. In general, this should depend on O and A. So what we want to argue is that for chaotic system, this will be independent of the details of O and A. This just varied generically.
Right. Generically, right. So there is some generic assumption like that. That's fine. I'm just trying to see.
Yeah. There's some generic. There's some generic assumption, but
right.
We are not doing any average here.
Right, but because one of the things you said was you want to understand what kind of Hamiltonian would generate typical states or generic states.
Yeah.
Is that addressed by what you're saying, or is that still an assumption?
No, so the statement I would say, just say for any say suppose, right now this is still a conjecture, but suppose we can prove this conjecture, saying that for chaotic system, the Hamiltonian evolution is such that for generic operator O and A, this is satisfied, and then.
Right. My question is just that because your operators were related to the density matrix that of the black hole, O was some density. So what's the guarantee that the density matrix will be generic?
By generic, we just say any operator which is not, say, here by generic, we mean really generic. Say if you have a product state, so the density operator corresponding to product state, I would say it's a generic operator.
I see. So generic does not mean typical.
That does not mean typical. Just means it's not identity. It's not some very specially designed, say identity here. Just say for example, your typical product states or typical non-equilibrium states, they should all be within this what we call generic.
Okay, thanks.
More questions, please.
Your consideration is actually does not seem to be limited to black holes. It's for a general quantum system with void formation, right?
That's right.
And would you expect that there is a one-to-one correspondence? Say the void formation is a necessary and sufficient conditions for appearance of such page curve.
Yeah, indeed. I think the so the page curve by itself is a very general statement. The page behavior is just a very general statement that if you take any subsystem, somehow you have this kind of behavior. And just in the black hole evaporation case, somehow these two geometric turnover. But this is very universal for general quantum system. But we just want to say for what quantum system you would expect somehow if you take some far from equilibrium state, the system actually can evolve into such a typical state. And say if you have an integral system, if you start from a far from equilibrium state, and then that may not evolve into such a state.
Void formation follows from unitarity, actually.
That's right.
Yeah, and so in this sense, chaoticity is not necessary. So just chaoticity is an example of models representing such a formation. Or you would say that chaoticity is also necessary.
So here is the statement. So indeed, the void formation by itself is just required by unitarity. But the key is that the pattern of void formation depends on whether this is a chaotic system or integral system. So for chaotic system, you have this generic pattern, which are independent of your details. They're independent of your operators, independent of the subsystem you choose. other than maybe some constraint from the causality. But for integral system, then the pattern of this void formation can be highly dependent on specific operators, highly dependent on the subsystem itself, etc. Yeah. Actually, we have a very explicit example of this. So you can study how this void formation affects, say, the entanglement growth of a system, say, after a global quench. And then you can just use these different patterns of the void formation to distinguish integral systems. The entanglement growth of the integral systems and the chaotic systems.
More questions, please?
I have another question.
Giuseppe, please.
Go ahead.
Okay, so probably, what would you expect? Probably you have some kind of bulk picture for random void distributions. I mean, for you say that it's quite general in that during operator evolution you'll have observe random voids. So probably there is some kind of bulk picture in additivity correspondence for random void distribution, or not?
Sorry, I didn't hear clearly the first part of your question. You say whether there's a bulk picture.
My question is, what is a bulk picture for random void distributions in operator growth?
You mean in the holographic?
Yeah.
We don't know the answer to this question at this moment, but in our paper in December, we looked at, say, the entanglement entropy growth, the time evolution of entanglement entropy for holographic systems, say after global quench. Okay, so if you look at some 1+1 dimensional holographic systems and look at multiple intervals, and look at how the entanglement entropy evolves for systems, say, for subsystems for multiple intervals. And then there were previous holographic calculations and give you a very complicated pattern, say, of time evolution of that thing. So we could show using very simple just analysis, say, just ballistic spread of the operator and this random void distribution that can actually reproduce that kind of pattern, which come from the holographic calculations. So that suggests actually this random void distribution is actually underlies the evolution in holographic systems. But how to see it explicitly, we don't have a precise picture yet. So does this answer your question?
Yeah.
Okay. More questions? If not, maybe I will ask, as I understand, you have presented a very nice general ideas about black hole radiations. I would like to ask you, do you expect maybe in future to derive some kind of spin black hole interpretation in terms from real gravity, to deduce spin Hamiltonian in some approximation from a real gravity Hamiltonian? This is a question.
Sorry, I'm not sure I fully understand. So you say whether we can deduce the boundary theory?
Deduce your spin system model from Hamiltonian, from quantum gravity Hamiltonian.
Yeah, that I think I'm not sure. That I don't know. So normally the gravity system we know have much more complicated boundary theory dual, have much more complicated boundary theory dual. So but I think that the general physics somehow, I think the power, say, like this kind of page kind of argument is very general. So I don't know. So maybe it's possible eventually yeah.
Okay, thank you.
Mhm.
I think the time is over. If there is some urgent question, please ask just now. Otherwise, we have to go to the next talk.
If I might ask, just understand that I get the picture correctly, you have to you assume that the full Hamiltonian of black hole and radiation is chaotic, right?
Yeah, actually, so you actually don't have to assume the radiation part is chaotic. So, so in this slightly more complicated model we considered in our paper, so you only need to assume the black hole part is chaotic. So the radiation part you can be free, can be essentially can be anything. Does not depend on the details of the radiation part. Yeah, in the pages discussion, actually the full system, yeah. But you can consider different models, yeah, and then the radiation part actually is not important, the precise time evolution.
Okay.
Okay. Let's thank the speaker again. Thank you very much, Hong, for your nice talk and answer to many questions. Thank you very much.
Okay, thank you.
Thank you very much.